Yeah. Okay. Hi, everyone. Good morning. Hope everyone's having a good day. So today, is going to so this is our first session of the day, and we're going to be taking a look at model comparison and interpretation. But since we have seen like advanced and introduction to interpretation, model interpretation on our last session, we're going to be focusing more on the comparison side, and we're going to have a demo on that one as well. So as always, if you have any question, if my audio is not clear, if you have like if my screen is not visible, please make sure to just tell me so that I can, yeah, I can we can continue with that. So let me share my screen first. So can you see my screen? I think this can help. Yeah. So yeah, okay, good. So yeah, so we're going to talk about model comparison and interpretation. That's more focused with the model comparison. We have seen it in our last session in detail, the interpretation and explanation part. So yeah, let's get to it. So first, what do you mean by, and why is it important? Let's talk about that first. So model comparison, of course, as the name implies, it's the process of evaluating and selecting the best machine learning model for a set of candidates based on the performance metrics. My voice is not clear. Is that from everyone, guys? Or I get some confirmation? Is it for everyone? Oh, okay. Yeah, okay. It was breaking. Okay. Sorry for that. Yeah. So I was just saying the process of evaluating and selecting the best machine learning model for a set of candidates based on the I think since I think we have been getting this. I think I remember in the discussion it's not been, so there is no favorite model. So there is no yeah, I'm just fixing my audio, so give me just a couple of minutes. Okay, so what about now? Is it better? Is it any better? Thank you for informing me, guys. Okay, so so there, I was just saying that there is no like good model. It just depends on the condition, on the problem that we are currently working with, and like the data, the conditions, the metrics that we are looking for, and so on. So it all will make sense in a bit, but I just wanted to highlight that like it's the process of evaluating and selecting the best machine learning model for a set of candidate based on the performance metrics. So there is no one perfect model for every case. So that's why we need to compare and evaluate and select the best one for that specific case. So why is it important? So selecting the most accurate model for a task, it will help you with that. It will help you with understanding the model strengths and weakness, and it will guide you to improvements, to make improvements, optimize resource usage, and time, your power, like your computational power, facilitates model improvements through iteration and refinement. So you will it will give you a roadmap into how you can refine and better your model and so on. So we do have some common methods that, of course, we're going to see in a bit. But these are cross validation, which is just assesses the model performance in a different data subset. The confusion matrix, I think you may know this in statistics, and if you have work with any model evaluation. So it just evaluates the classification of accuracy, but with true positive to false positive, true negative, and false negative. And our ROC curve and AUC are just the measurement of between true positive and false positive and so on. And of course, the three evaluations, which are precision, recall, and F1 score. And of course, you can also add here as sensitivity. I think you can call that recall, and specificity. I think, yeah. But yeah, so you can also have those. It's just as a part of recall. And so one example is just spam detection. So comparing models to help you select the one that minimizes false positive. So false positive means if a spam email comes in, so it's a negative, but the model sees it as a positive, so it's going to harm you. So that's called a false positive. So it's not a positive, but it mistakes it for a positive, so it will give you the negative as a positive. So we will see the confusion matrix as well. And yeah, so these are some just common methods and examples of how we can compare a model. So why we do this? So it's more important than building one model. So modern ML or machine learning involves many experiments with different algorithms and configurations. So the goal here is to find the best combination of algorithms and data for your specific problems. So some of the key benefits is enhanced performance, extended lifetime, streamed retaining, which is good documentation from the comparison, accelerated production, and cost efficiency, because it will reduce unnecessary experiments, saving you time and computational resources. So why do we choose like the best model? So it's a balancing act, not just a single criteria that we will take into account. So as we have said, we may have different or multiple matrices that will help us to choose the correct or the best model for our case. So if we are looking for performance or how accurate it is, we may take a look at the F1 score, the precision, and the recall result to choose the best one. For our case, if you are looking for computational efficiency, so you will see how much resource they take in. It could be training time, inference speed, or prediction time, memory usage, energy consumption. So if you are looking at the computational efficiency, you will just see these matrices. If you are looking for generalizability, how well does it perform on a new and unseen data set? So this will help you avoid overfitting. And how interpretable is it? How is it? Yeah, how easy is it to understand, and why? I think we have seen this earlier on the last session. It will just help you understand the process you went through to give you the decision or the result that you are looking at. And of course, the last one is business context. So what are the project constraints, the type of the problem, the quality of the data, the deadlines, scalability needs. So based on these things, based on these criteria or like matrices, you can go on and choose the best model for you. So we will have some scenarios where like where you may need the performance metrics more, if you need the computational, or like actually really have the time. So if you are more focused on time, which model you should go with, and so on and so on. So we will see these things in our example. Okay, so let's see one essential matrix, which is the confusion matrix. So here is just a simple table where the model gets things right and where it gets them wrong. So here, actual positive, so the result of like the actual result of the test data set. So it's a positive one, and you're predicted if it is a positive. So that means it's a true positive. So it has correctly identified the positive, and here if it is a negative, and if your model predicted a negative, it's correctly rejected or identified through negative. But the danger lies in these two like boxes or cells, because here is actually positive, but it has predicted it as a negative. So it has been missed by the model. So here you can take an example on the earlier. So if it is a legitimate email, but your model sees it as a spam and puts it in a spam folder. So that's a good example of this. And here, if it is actually a negative, actually it's a negative, but it's seen as a positive, it's a false alarm. So if it is like the reverse of that one. So another example is if it is, for the example that we're going to see when YTP and FP happen. So false positive and true positive. So that's what I'm trying to explain. So false positive happens when it's actually a negative, but your model predicts as a positive. So for example, if you don't have like, if for example, the example that we're going to see is the breast cancer example. So if the model predicts as a positive, which is it has like if the model says it's a cancer, but if it is not a cancer actually, so that's going to be a false alarm, right? So that's a false positive. And for the true positive, if it is actually cancer and the model actually predicts a cancer. Yes, I think you're trying to clarify the question. Please go on. Balada, you're on mute if you are speaking.
Okay. Thank you. Sorry for interrupting you. I mean that what the cause for that, especially we don't need, I think, the false positive one for our interpretation or for our result or anything. So what the cause of this false positive?
So I don't understand. Why don't we need it? Like the question is not clear for me. So the false positive is if the model predicts it as a positive, but it's actually a negative. So I don't understand the question. Can you repeat it? I think.
I mean that even let we say it's okay, we need false positive or false negative. But what is the reason this one has happened is that it is because of the our data, or what is the cause behind that?
The model. So we are talking about it. So you have built your model, right? And you are trying to test the model. So when you're testing it, you compare it with the actual result. So for example, if the model, like you give it the test, like the test data, so you give it the features and it gives you the result, right? So after you give it the features and the result comes out to be positive for a cancer, but the actual result that you have is not a positive, or it's a negative, it's not a cancer. So that's called a false positive or a false alarm. So we do need it. So it's after the model. So you're testing the model, how good it is. Because it's from here that you get, the precision, like the recall, the F1 score, and so on and so on.
Okay, thank you.
Okay, I think so we will see actually the example, so maybe it will be more clear there. But thank you for the question. So for the false positive, and okay, let me just get Amdemkel and we will continue. Yes, Amdemkel.
When I see the two bulletins, the one is false positive.
Yeah.
It's a flagging a legitimate transaction as a fraud, but
Yes.
false positive means actually the email is actually negative, but it's predicted as positive, right?
You mean the ML, you mean the data, the actual result?
I'm reading the table, condition matrix table, when I trace.
Yes. Yes.
It's predicted as a positive, but actually it's negative, right?
For the false positive, you mean? For the false positive, it's actually a negative, but it's predicted as a positive. No, actually, yeah, it will be the reverse, I think, yeah. But it's correct, yeah. So for the fraud, I think you're talking about the bullet point. So for the false positive, which is a type 1 error, so it's flagging a legitimate, so that's a true, but it's so it's actually a negative, but actually considering it or flagging it as a fraud.
So in this means, negative means it's actually is not fraud, it's a legitimate email, right?
So here for the example, it's trying to so let me just give you a context for the example for the bullet points. So positive means it's a fraud. So positive does not mean like, don't take like the positive and the negative as meaning positive means good and negative means bad. So you're trying to detect whether or not it's a fraud. So positive means it's a fraud.
Okay.
But negative means it's not a fraud. So if you take it as a base, like if you take positive as a good and negative as a for like a bad thing, so that's not correct. So false positive means it's a legit, so it's a negative, it's not a fraud, but it's considering it as a positive, as a fraud.
Okay, I got you.
Okay.
That's what I see.
Okay. So I think yeah. So that like I think for like the example, having a fraud is a positive. So we are positive that it's a fraud, but if it's a negative, it's not a fraud. So maybe I should have given that context. And for like the earlier example for the breast cancer, so positive means it is a cancer, and negative means it's not a cancer. So that's why like the false positive is alarm. So because it's actually not like a cancer, but the model is telling you that it's a positive, that's it's a cancer. But yeah, thank you for the question, Michael and Beletta. But let's continue if there is none. Okay, so let's go to the the precision, the recall, which are the strategic choices. So the best metrics depends on the cost of your errors. So here we will see some errors. So the precision is just the true positive. So of all that time we predicted positive, how many were them? How many of them were right? So here it's just the number of total positive divided by total positive plus false positive. So we have the total positive, which is we have predicted that the true positive and the false positive. So and we have the actually true positive that we have detected. So how much of the total positive are actually a positive? So that's basically what it means. And you can also see the formula here. So the cost of when to use this. So when the cost of false positive is high. So if the cost of false positive is high, you should definitely see this. So an example is if you don't want important emails landing in the spam folder, especially for the fraud detection, it's really bad, or it makes you very like it's not a good look if you predict or like flag legit transactions as fraud. So the cost of false positive is high here, so that's why. And recall or sensitivity is just of all the actual positive case, how many did we find? So it's just true positive divided by true positive plus the false negative. So when the false negative is high, we should definitely use this, because if like for example for the fraud detection or for the disease screening, we cannot afford to miss a case. So if it is a fraud but the model flags it as like a legit transaction, so that's called the false negative. And if the cost is very high, that's when we should use recall or sensitivity. And no, specificity is just the reverse of this. When the cost of false positive is high, we will use it, and we will actually see it in the example. And accuracy is just the true positive, and just how much of the prediction were correct, how much of like of the all predictions, how much of them are correct. So here we can see that the true positive and the true negative divide by all of the predictions. So accuracy can be like very misleading in an imbalanced data set. So I have actually used an imbalanced data set to show you this, and actually how to solve this, or how to account for it as well. A model can be predicted as non-fraud in a dataset with 1% fraud. Will have 19% accuracy, but it could be completely useless. So if there is an imbalance in the dataset, we should be very careful with our interpretation. And for the F1 score, it's just 2 times precision multiplied by recall divided by precision multiplied by plus recall. So you use it when you need balance between recall and precision, especially when imbalance when using imbalanced data set. So we will also see this. So actually all of these can be like, you don't need to have the formula in order to perform them in Python, but it's just good to know. That's why I have included it here. So we will also see these 4 things, including the the conversion matrix in the example. And the AUC ROC curve are just a metrics classifier performance, especially on an imbalanced data set. So the ROC curve are just a plot of true positive rate, which is the recall, against the false positive rate, which is the specificity at various decision threshold. And the area under the curve, or AUC, is just a measure of entirely 2-dimensional area underneath the ROC curve. So if it is a perfect classifier, you have a 1, no better than random chance, 0.2, and if it is greater than 0.7, you can generally consider it as an acceptable model. So it gives you a single number that summarizes the performance across all thresholds that we have seen earlier. So it's good. So before you compare, for the comparison to work or to be valid, you should actually set up a verified. So you should ensure that the data is standardized, especially for NAM3 algorithm, models, because all models must be trained and tested on the exactly same data splits. So the randomness you should actually have. Sorry, let me just. Yeah. Okay. Yeah. So yeah, you should have the same dataset split for all of them, because you will this will actually ensure that it's repeatable easily. So sorry, I think, yeah. Okay. And consistent evaluation. So use the same evaluation metrics and protocols for every model. Experiment tracking, you should record everything, the time took and everything, the parameters. Yes, Nabil, is that a question? The parameters, the complication, and the code,
I was
and everything.
I was just sorry, I was just gonna say, for those who don't know, the way you keep it the same is you just set the seed at a consistent number across all your experiments. So if you have the same training library or whatever, and you set the same seed, you'll get the same result all the time, just for
Yeah,
purposes of comparability.
the random state. Yeah.
Yeah.
Yeah. Okay. I think I think I was planning to go through it on the demo. That's why I didn't mention it. But yeah, thank you for sharing, Nabil. Okay, so it's really crucial for for the case of reproduction and reproducibility and debugging, that you do the same thing for all the models. And lastly, so the model with diagnosing the model with learning curve. So you can plot the performance, the loss and the F1 score against the training dataset size or input, which tells you how the model is learning, so that you could you could see if there is a high bias or underfitting, or high variance, which is overfitting, or in between, which is just right, where the training and the validation score converges at a high performance rate. I think, yeah. So it's also good to see this. If there is a huge gap between the high training score and low validation score, the model memorizes the data and it's not generalized. So it's going to work for the data you have, but it's not going to work for, it might not be good for the other, the data it has not seen. And if it is underfit, both the training and the validation score are very low. So it's the model is very, very simple, and it's not going to be able to tackle or give you a good prediction. So having it just right is a good practice as well. So lastly, the key takeaway here are the model comparison is very essential. So it's a very strategic process that goes beyond the single metrics to imbalance performance, efficiency, and real-world constraints. So you should choose your matrices very wisely, because you should select the matrices precision, recall, F1, AUC, and so on, that align with your business goal and the cost of the different errors. So there will be error, but which one is more, which one do you want to avoid the most? So the best model, of course, there is no one best model. It just depends on your need and case, but it's the one that meets your project's unique needs and so on. So that's it from the the presentation side, the theoretical side. So is there any question? Is there anything that's not clear? Please let me know so that we can go through them. Questions, or is it clear, guys? Yes, I think there is a question. Yes, Nabil, I think.
Yeah, I just wanted to ask what's the best way of measuring success of class balancing? So sometimes I have a little bit of difficulty knowing, should I do class balancing maybe 1 to 2, 1 to 3? Which one is the most fair and which one is the most statistically rigorous, I guess, if I should make sense. Is the most defensible is a better way of putting it.
I don't have like a good strategy on top of my head right now, but having a matrix, I think, is a good way. So finding a balance. So we will see it in the example, but why would I do is I would just have a matrix of what I need to see, and depending on that matrix, I just rank them, if that makes sense.
Kind of. Are you talking about, I forget what they call it, but it's one of those K methods where you optimize your hyperparameters. You mean something like that?
Yes.
Like K folding or something like that?
Yes, I think I also forget the name, so that's why.
I think you're talking about K. I think you're talking about K folding.
K,
Yeah, K fold. Yeah,
the,
K fold cross. Yeah, K fold cross validation.
yes. So I think
Yeah,
we can go through that.
that's what a lot of people do.
Yeah, yeah. I think that's the best one that I have so far. But I think it's good to experiment with others as well, if there is any.
Of course.
Yeah. So what do you use? I think you were talking about it as well.
I was just saying, for me, I use sometimes K-fold validation. I just don't like it because depending on the model that you use, it can use a lot of computation power and training and trying all the different hyperparameters to tune your model can be very time consuming. So I'm trying to understand from first principles if I can somehow cut a little bit of time in hyperparameter tuning.
Yeah, it's a bit complex. So it's just a trial and error for sometimes. Like you know, it's a very computational and time consuming. But I think that's I just plot I just try to plot you know, like the parameters against their efficiency and like the accuracy and so on against the metrics, and see try to find that elbow and just work with that parameter. But of course it works with like very small data set, but as the data set grows, it's a very bad practice.
Yeah, I've been there before, waiting 4 or 5 hours.
Oh, of course. It's very bad, but for demo purposes and so it can be done for small data sets. Yeah. Okay. Yeah. Okay. Thank you, Nabil. That was a good question. Kevin.
Okay, my question is, we've seen different ways to test our model, and can we use it for every model? For example, can we do recall curve or F1 score for every model? For example, let's say we have a language model, so can we use for every model that we have? That's my question.
No, the evaluation methods are not for all, of course. You cannot for instance for interpretation and explanation of the model. So it's not like one method could not work with the other. So that's why it depends on and the model type and so on. Yeah, but for the model, for generally like the models, you could do these things. If you can evaluate them, you can definitely like draw these curves. But I think that's a good question. I think I haven't thought of it as that before. Interesting.
So what do you suggest for the current project that we have? Which evaluation technique can we use?
I think you can use, so like you have the trained dataset and you have the tested dataset and so on, right?
Yeah.
So you can definitely like evaluate them with these techniques, I think.
Okay.
I will definitely take a look at them, but you should be able to, yeah, you should be able to do this.
Okay.
This is for general models, but you should be able to do this as well.
Okay. Thank you.
Thank you so much for the question. That's interesting. Yes, Nurie?
So my question is, in our last project, we have tested or evaluated different models for classification and regression work. So in regression models, it's okay to identify which model is good and which model is not good, just by identifying the RMSE and R-square value. But when we come to the classification models, we have accuracy, precision, recall. But most of the time, when we try to calculate the accuracy value of one model is good, and the precision is not good. For the other one, the precision is good, the accuracy is not good. So how are you going to compare the final result, which is good and which is not good? Like, have you get my question?
Not quite. So I think you were saying that you have chosen different evaluation techniques for different models, and how do you compare them with that? Is that the question?
Yeah, in classification models, we have accuracy, precision, recall, right?
Yes. No, you can use them as for tree and as others as well.
For what? For whom?
So you can use this like accuracy, precision, and so on for other models as well. So which models do you think you cannot use them for?
I mean, we are using this for classification models, right?
Classification models, yes, okay.
Yeah, so what I'm saying is, if one model have a good accuracy, but somehow bad precision, and the other model have a good precision, but somehow bad accuracy, how are you going to compare it final result?
Okay, oh yeah, okay, that's a good question. Yeah, so as I've said earlier, so it depends on what you can what is your like what error are you more sensitive to, right?
Okay.
So if you are more sensitive to like false positive, so that was what I was trying to explain here. If you can see here, so if you are more sensitive to false positive, you should consider, or you should like choose the high precision models. But if you are more sensitive to like false negative, you should use the recall, like the one with a better recall, or the one which is more sensitive. So you're going to choose the model based on your metrics. So did I get your question?
Yeah, I got you.
Yeah, so it depends on your use case, or what error you are more scared of, basically. Yeah.
Thank you.
Good question. I think I missed it on the first go. Yeah. Okay, that's good. Anyone else? Any questions? Okay. Is that okay? It's clear, I think. So I think we should move to the demo part. So can you see my screen? let me just zoom in a bit. I think it's not better, guys. Can you see it better now? Okay, good. So what we're gonna be working with is actually, we have seen this model earlier on the last week's session. So we're gonna see the breast cancer dataset, where we have the malignant or positive and the benign results, or the targets, and it has an imbalance where we have a total of 569 samples, and we have 30 features, and of course a slight imbalance between them, where we have slightly higher benign targets than the malignants, which is the positive ones. So I wanted to work with an imbalanced model, because when you work with, like financial data set, fraud detection model, which you will be working with in the future, you can expect that there will be an imbalance where there will be smaller, results or targets for, fraud, positive fraud, more than the negative ones. So I just wanted to work with, because it will help you be more familiar with it. So yeah, let's go to it. So here I'm just importing the required libraries, and here I'm just loading the data set, and here we can see that there's a the data set shape. So here we have, as we have seen, like we have 569 samples and 30 features, and the one is just target. And here for the distribution, you can see that there is an imbalance where 212 for the negative or the benign, and for 357 for the positive one. So here you can see that the imbalance, you can actually see the imbalance. It's just a plot of just to show the imbalance. And here for the pre-processing, so I used the random set of 42, which is the seed, which was what I think Nabil was implying earlier. And here I have chose to stratify Y, which is just means I just tried to have like a constant, or at least somehow approximately equal or close sample percentage between the test and the train, because there is some imbalance between them. So I just wanted to have represented the sample equally in the test, and in the train dataset. And I have used 80% of the dataset to the train, and just 20% to the test. So here you can see the distribution. So here for the test we took 455 samples, and for the test I just took the 114 samples, and the features is constant. And here you can see that the percentage of benign here is 37.4, and here it is 36.8. So it's approximately or very close to each other, not like it's represented fairly in both, for both of the the targets. And here what I've did is I have scaled the the value, the features, because for, of course, for random states, for the random forest and for others, it might not be very important. Yes, Fabian?
Can you explain more about the taste and the training data percent? I don't understand what it.
So here, this one, you mean?
Yeah.
It's just like, it's not the percent. So we like, I have, you mean the stratify. So here I have used stratify Y. So it means like it's going to try to represent the targets equally in both the training and the traced dataset. So here in the training dataset, we have 170 bannings, which is 37.4% of the whole dataset. And here on the test as well, it has 42, which is 36.8% of the whole dataset. So I'm trying to represent them as closely as much as much as possible, to be closely to each other, so that they are represented equally, because there is an imbalance in the dataset that I'm trying to do this.
So the imbalance you were talking about, is it between the training and the test datasets, or the whole?
No.
Uh-huh.
No, like when I said imbalance, so there is an imbalance. So here, if you can see, there is an imbalance between the malignant and the benign.
Okay.
So here, like we have more malignant and less benign targets in the dataset. So there is imbalance. So when you work with fraud detection models, when you take a look at fraud dataset, there will be even higher imbalance, because there will be more non-fraudulent transaction more than the like the fraud transactions. So there is imbalance, but I try. So here with Stratify, what I try to do is to try to represent them like at least in percentage equally in between the training and the tested dataset.
Okay, I get it. So we also have to balance the training, the test.
Yeah. So here is what we did. So I think I don't think you like got me. Okay, is that clear, Fabian?
Yeah, I think I understood what you meant.
No, like okay, like say back to me maybe.
So the balancing, the imbalance was between the data sets overall, not between the train and the test. But when we tried to, classify it as training and test, it was balanced. Yeah. We also have to balance the percentage that we have.
It's not a have to, but it's good for the training.
It's good to have. Okay. Yeah. That's what I get.
Yeah. Okay. Good. Yes, Nabil, I think you wanted to add.
I just wanted to add a little bit. I was going to say generally it's best practice to do about a 70-30, 80-20 split of testing to training whenever you're doing your splits. The reason is because you want to be able, especially if you have enough data to work with, you want to have enough data to test on that your testing is has statistical significance. So generally people lean on having about, I would say, that kind of ratio, kind of like 20 to 80 between the training and the testing, or 30 to 70 are the most common ones I see. And yeah, when you're just doing the class balancing, you're just balancing the positive versus the negative actual results. That's all you're doing. So the two are very different things that you can't really talk about in the same sentence.
Yeah. Okay. Thank you so much, Nabil, as usual. Yeah. So is that clear, everyone? So it's a really interesting thing that we have. It's been raised. Yes, Abdulmikhail.
Maybe I got some confusion about Nabil's explanation. First, statistication and splitting training into tests. The models are two different things, in my understanding. Are they the same thing? Because
No. So the question is splitting and stratifying the same thing? Is that the question? I didn't get it.
Yes.
No,
Because,
it's not. So, okay. Continue, please.
yeah, I mean, stratification means subgrouping those data into some kind of subgroup, right? Uh, and splitting the data into testing and to another training and testing groups came after making our data.
Yes.
So I mean,
Yeah.
maybe
You
I
are
use explanation of enable. That's why.
no, Nabil actually like try to explain two different things on the same time. So that's why. But he exactly said that what he has said. So he just was explaining why we choose like training the split of like using 80-20 and 70-30. So that's what he was explaining, not the classified part. On my understanding, at least. Yeah.
Okay. And
That's
also,
exactly right.
and also, I have seen additional way of splitting the data into training, testing, training, and verification. Is there any splitting three parts of the data? First, training, then testing, and finally, we will use the data that not exist in training and testing in order to verify. Is there any such kind of practice?
Not that I know of. I think I usually like use a separate data set for validation, not that one that's already splitted for my experience. Okay. Okay, good questions, guys. I really enjoy these things. Thank you for like keeping the conversation flowing. Thank you, everyone. So like I was talking about scaling. So I used scalar because I wanted to scale the dataset for, just for the logistic regression. Because it benefits from it. It's not a tree, like algorithm. So it benefits from, it depends on the scale or the values. So I just scaled the X training, the X test dataset. So I just fitted transformed the train on the train dataset, and I just transformed it on the test dataset. So I didn't fit and transform on the X dataset, so that would actually cause leakage. So after that, so here you can see before it was so basically it's going to be between -3 and 3 after you scale it. So here you can see before scaling and after scaling. So I'm going to use this scaled dataset on the the logistic regression model, and for the rest I'm going to use the normal just to see how different it's going to come out with. So here I have decided to go with 3 models: the logistic regression, the random forest, and the gradient boosting models. And for all of them, I used the same seed. I used 42 random state just to keep what we have discussed earlier. And the number of estimators is for the 3 algorithms is the same, which is 100. And for the logistic regression, I just used the maximum iteration of 1,000. So here, what I'm going to do is I'm going to have a dict that's going to store the results. And here, yes, is that a question? Why do we need scaling? So since the values are like, if you can see it here, there is a big difference between the features. So here you can see for the radius it's very high, and for the mean compactness it's very low. So there is a high difference between them. So we need to scale them in order to, you know, like make the model like the training better, and for the testing and so on and so on, for logistic regression at least. So it's going to scale everything into, you know, like mean, I think value minus mean over standard deviation. So that's the formula it's going to follow. So it's going to calculate the mean of the mean and the standard deviation of each feature, and it's going to subtract the value from the mean. So sorry, it's going to subtract the mean from the value and divide by the standard deviation in order to find the scaled version of it, so that everything is going to be in the same range, and it's going to be easier for the model to, you know, like learn on and predict. If that makes sense or not, I'm doing okay. So you can see here for the third feature, it's very high, if you can see it. So it's very high, so it's not going to be good. So it's going to be scaled to here. So it's like scaled very low. It's going to be in this similar scale. So what I did basically is I just used the scaled for the logistic regression model, and for the I just used the unscaled. Yes, sound okay?
So can you scroll up again on the scaling part?
Yes. Here?
Yeah. I heard you saying that we are scaling between -3 and 3, right?
No, we are not. So normally the scaled version could be in between that range, but it's not a must, of course.
Okay, so
we didn't decide on the number.
Okay.
So it depends on the data set, not on a predefined number. If we normalized it, of course, it's going to be between 0 and 1, but we didn't normalize it. We're just scaling it.
When I see the scaled records, the second row also greater than 3. That's why.
Okay. So it's just like a, you know, like a, yeah, I can see. Okay, so we have these things. So I just used for the normal, and so for the models other than the logistic regression, I just used the normal, like the unscaled method, like data, because it doesn't really matter for the rest of the tree-based models or the tree algorithms, but for the logistic regression, it matters. So I just used the scaled one for it. And to measure the training time, I just used the time, the current time as a starting time, and try to, you know, like fit the model, train the model, and at the end I just took the time and subtracted from the starting time. And for the prediction time, I just used 100 of them, and I just I don't need the prediction, so I just ignored it. I just wanted the time it took to make the prediction, so I just used that time and saved it in the prediction time. And for the average, I just used the mean of the average time, and for the prediction per sample, I just used the average prediction time and divided by the length of the X test model multiplied for 8,000, which is millisecond per sample. So here, and then I just used the prediction, and I'm going to use this Y prediction for, you know, like for the future evaluations. So we have the test, the model, the Y prediction, the training time, and the prediction time per sample. So you can see it here for the logistic regression. It took 0.074 seconds to train, and the average time per sample was 0.0012 milliseconds. And for the rest, you can see them here. So it's higher for the gradient boosting model, which is expected. But for the prediction time, it's higher for the random forest than the others. And here for the evaluation, I just used the accuracy score, the prediction score, and the recall score, and the F1 score methods in order to find the values for every model. So here you can see the results for each one of them here. So the accuracy, 98%, 0.25, the precision, the recall, the F1 score. So it's basically close to each other for the training time and the prediction time. And, for the random forest, you can also see the results. And for the gradient boosting, you could also see the time. And for the comparison, you can see this simple table where you can see that the logistic regression is the more accurate, the more precise. It has the higher accuracy. Actually, recall actually it's the same as gradient boosting, and the F1 score, which is higher than the rest. And also the training time is the best, but and as well as the prediction time per sample. So here is just a comparison of visual comparison. So here for the recall, it's the same for the gradient boosting and the logistic regression, but for the rest, it's not it's better. And here you can see the performance versus efficiency trade-off as well. So I'm just going through it. So here I have the sensitivity and specificity results, as well as the confusion matrix. So here you can see out of the total samples, the random, the logistic regression has identified 41 of them to be true positive, and 71 of them to be true negative. And here you can see the errors it has made. And here as well, you can see it has made more errors than the others. And here as well, you can see how it has affected its specificity. So it has identified the actual positive to be a negative. So if you are more sensitive towards that, you should avoid using the gradient boosting and so on. So this is for, I think it was asked earlier, so you can see that. So here, I think it's just more explanation on what we have seen right here. So correctly identified the positive, which is the range. You can see 41 and so on. And for the sensitivity, the detection rate of Mallinjant and the detection rate of Benage and so on. So you can see the results here. And with the interpretation, we have seen this on, I believe we have seen this on the earlier sessions. So that's why I didn't spend a lot of time explaining it. But for the three based algorithms, models, you can see that they have these feature importance. So here you can see for the random forest, it's more dependent on worst area than the worst radius. And you can just see how important they are for making the predictions, how, on what it depends on. And here as well for the logistic regression, you can see that the worst texture is the highest prediction feature. So here you can see, so what I did was I have created, oh, where is the notebook?
Expand it.
Yeah, I'm trying. my computer. Sorry, I think I forgot to expand it. Yeah. So here is just sorry, it's not going to work because I didn't run it from the start. So what I did was I just had these scenarios where for high performance priority scenario you would want like accuracy, high precision, high recall, and high F1 score. But you might not be that much, that much interested in the time, like the amount of time or the resource it takes. You just want to have a high performance priority. So in that case, I just give 25% for the accuracy, the precision, the recall, and the F1 score, and 0% for the time it took for training and prediction. If you are concerned more about speed, a high speed priority, so I just give 30% for training time and 30% for prediction time, and just 10% for the evaluations. And for medical applications, we need high recall, which is prioritizing catching all the cancer cases, so having more higher recall. So I just give like the accuracy and the precision 15% for the recall, higher percent, which is 40. And for the F1 score, I just gave it 20% because it's also have the recall. And for the training time and the prediction time, it just 5% each. If you prioritize, like if you want to find a balance between time it took to train, it took for prediction and the evaluations, I just so this is just a scenario that I came up with. Okay, so it's not a must, but for each case, I just wanted to find the results, or which model is the best for each of these cases. So it's just going to random and multiply them by these scores. And okay, I have to run all of them, but it's not going to take time because it's a very small data set. So here you can see, since it has a higher performance for especially for the evaluations, so it gave it 100% for high performance priority. For the logistic regression, for the gradient boosting, you gave it 25%, and for the random forest, it just gave it 7%. So it's very low. And you can also see how it goes, but you can also change up the weights of the scenarios in order to find the best and the one that's going to work for you. But yeah, basically it's just for the scenarios. And here is just a highlight or a summary of what we have seen earlier. So the percentage it give for accuracy rank out of 3 being the worst and 1 being the best. So if you are looking for precision, so the gradient boosting is the worst model. But if you are looking for rank, for recall, the random forest is bad, because if you can remember, it has the lowest recall. For the F1 score, if you are looking for a higher F1 score, the random forest is not your choice. And for time, the gradient boosting actually took a lot of time. So for average rank, you can see that it's the logistic regression is the best one for our case, at least. And the gradient boosting is the second ranking, and the random forest is the third. Of course, you can do some parameter fine tuning and so on in order to betterment the other models as well, and get a better result into the scenarios again. So overall accuracy, so for the logistic, it's higher. The fastest is also the logistic. The fastest prediction and training is for the logistic, and for the highest recall, which is for best for medical cases, you should use the logistic regression. Yeah. So if you are looking for a general purpose, you might go with the more balanced one, which is random forest. But for the rest, it's the logistic regression. And here you can just read how to, like the trade-offs, what are the trade-offs, what are the multi-dimensional evaluation, and so on and so on. So it's just an explanation of what we have discussed here. Yeah. So how was it, guys? Was it clear? Is everything clear? Is there a question? Okay. I think who has confirmed what about the rest? Is it clear? Okay, good. So I will take that as a yes. I think we have actually took a lot of time. We have gone over time, but it was a good discussion on my end. Thank you guys for participating and asking questions. Thank you so much. I will be sharing, so I think I can already share the slides here, but I will also share on the drive, so be on the lookout for it on drive. Yeah, thank you guys. Yes, Nabil, or was that a mistake? Okay.
A mistake on my part.
Okay, it's okay. Thank you guys. Thank you so much, and have a great day. Bye.